Thank you very much for the nice introduction. Ladies and gentlemen, my talk today is about conceptual design of long-span bridges, excited by the wind and waves. During my career, I have had several roles in projects. I've done detailed design of steel and concrete components, and then finite element method analysis, both in time domain and frequency domain. And I have worked as a project manager on long-span bridges. Today, I'm going to show you one way of doing design of bridges excited of both wind and waves. Many years ago, I was on a vacation with my family. We arrived at the site very late at night and went to bed. And early in the morning, while still dark outside, the room started to shake. And it escalated fast. Earthquake. Now, coming from Norway, we are not used to that, and that was the first time for me. And we grabbed our kids, and we decided to stand at a stiff point in the structure, thinking that would create an air pocket in case of collapse. So we're standing there shaking, listening to what sounded like a freight train running through the floor below us, accompanied by concrete elements rattling on its support. Counting seconds, which is a proxy for energy release. Now, the whole hotel evacuated out quietly into the dark onto a small hill next to the ocean. And this was a few years after the Indian Ocean earthquake with a devastating tsunami. And you can see that everybody was looking onto the ocean and thinking the same thing. Now, after a long time, we were allowed to go back into our building. And at that point, I was very grateful that this country has a comprehensive design code in respect to earthquakes. Because the magnitude of this earthquake, as seen on other places in the world, will completely level the buildings to the ground. Now, back into the room, I was a bit curious. And I went to the wall that we were lying on, and I knocked at it, and I discovered that that was a non-structural wall. So the point of this talk is safety of structure, and that is that you and I have a responsibility of making safe design, even if it's not codified. And that is the core of my talk today. I'm going to talk about ordinary long-span bridges, what happens when we make them longer and put them into the water. I'm going to show that we need extensive measurements of the mid-ocean data, and I'm going to show how we can transform that into load on the structure, and also how we can extract the important design parameters for these from a huge amount of data. And in the end, I'm going to talk about some promising technology for wind engineering. Let's look first at some of the basic design concepts. This is a very simplified picture, but what we usually do is we get a load requirement from our client, for instance, specifying a return period of 100 years. We take these loads and calculate the forces in our structure. And of course, we want the forces to be smaller than our design capacity. To take into account uncertainties in material and workmanship, we reduce the capacity with a material factor. And to take into account uncertainty in our load, we increase our load with a load factor. And the total safety for this type of structure is typically around 2, which I think is a comfortable level. So, when we start out the design, we get the design requirement from our client. And these are typically functional requirements. It will tell us the number of lanes, it tells us the size of the navigational channel, and it also tells us a little bit about the loads. It will also tell us a flutter criteria, which is a criteria that makes sure that the bridge has a sufficient safety with respect to high winds. Now, for long-span bridges, which spans more than 1,700 meters, we normally need to do double decks. This, of course, has a big cost impact on the structure. It will change the size of the main cable, it will make the tower wider, and we need a little bit bigger anchorages. They also specify comfort criteria, typically in the form of acceleration. And then vortex shedding becomes important, and we might need to change the cross-section a little bit to make it work good with respect to vortex shedding. Also, we have vibration of individual components. And this needs to be mitigated unless it can become a maintenance issue. So in the following part of this talk, I would limit myself to wind loads of the buffeting type, as that is the load that got into our design in the US forces. Now, if we extend the span, long span bridges, the price of the structure increases exponentially. So it, of course, it becomes interesting to put the towers into water. And we put them into water, they are affected both by static loads and dynamic loads of the water. And as we get deeper, the foundation becomes more and more complex and expensive. And at some point, it will be of interest to see if we can use water as support. But then we also have dynamic structures in water, and we have to take into account the dynamics of the waves. The dynamics of the wave have a different frequency content than wind and earthquake. It also mean that we have to take into account hydrodynamic effect of the floater, giving added mass and added damping to our dynamics. Here is a comparison of the frequency content of the different loads. The blue line is the wind, and the green line is the earthquake. And you can notice I have split the waves into two groups. One is swell, which is associated with storms far away from the site. And the other is wind-driven, which is associated by weather system passing the site. And if you relate this to our typical long-span bridges, we have frequency in this range. And of course, if you have the towers on land, you don't have to take into account wave loading. For buildings, you will see that they are more sensitive to earthquakes. But if we then move into the water, looking at jackets, GBSs, or caissons, we get frequency that starts to pick up wave dynamics. If you move further out into the sea, we find TLP structure, tension leg platforms, which is typically gas and production facilities connected to the bottom with steel tubes. These are more flexible, and the typical design of these is to try to separate the lowest frequency away from the swell like this. Now, if you go back to the long span bridges and start to make them longer, you get more of the low frequency part, lower frequencies. And since we have a superstructure on top of this, for instance at TLP, you have a lot of modes related to the superstructure, and it makes it impossible to design yourself out of the swell. So this needs to be taken into account into our design. I'm going to show two examples. They're all related to the E39, which is a highway, planned highway along the western coast of Norway with the purpose of reducing travel time. The road crosses many of the widest and deepest fjords in Norway, and these concepts I'm going to show today is possible to use for several of these crossings. So this is the Sulafjorden. It's a typical Norwegian fjord. It's quite wide, it has a complex surrounding terrain, and steep faces down that continues down through the water. The water basin is quite exposed. Down to the left of this picture, you find the North Atlantic Ocean. And the fjord is only sheltered by some scattered islands. Our client, in an early phase, identified 4 different possible alignments, ranging from 2,700 meters at the fjord entrance and 4 kilometers further into the fjord. And the depth of this fjord is around 450 meters, and quite flat in the middle. So they wanted us to explore 4 different concepts. At the front is a one-span suspension bridge with a main span on around 2,700 meters. This is a little bit shorter than the planned Messina bridge. Then you have 2 concepts with fixed bottom foundations, and then there's a TLP structure, which is what I'm going to talk about today. This multi-span TLP structure is supported by floating foundations. And these foundations are supported by tension leg and suction anchor, and combined suction anchor and mass anchor at the bottom. This video shows a typical installation sequence for that system. Tension is added to the system by deballasting the floater, as shown here. Now, having a multi-span bridge, we use steel towers at the floating foundation. The steel towers is chosen because of low weight, so we want to minimize the weight. But the main problem with a multi-span suspension bridge is that you can have different loads on different parts of the span, and that creates unbalanced forces over the tower. And these has to be balanced out, and during that balancing, you have to adjust the tower stiffness. And I think overall, we have found a good balance between structural design and aesthetics. And seen from the sea, when they're coming in, you can see that the towers are around 200 to 230 meters, and it's a quite transparent scene from this angle. And it also accommodates the largest cruise ships in the world. So here is the 4 alignments. And then at the beginning of the project, more than 8 years ago, the client asked us and said, we want to understand the mid-ocean climate in this fjord. How do you go about to do that? And we specified a measurement program consisting of 4 meteorological wind measuring masts placed at strategic location compared to where we can expect towers. We also added wave buoys, both permanent and temporary. And some of these buoys measure current, salinity, and temperature all the way down to the 450-meter deep bottom. I would say that the measurement campaign has been very successful. We have been logging 24/7 with up to 10 hertz, and we have data for 8 years. And we look at the quality of the data, we find that 99.9% of the 10-minute mean values are quality controlled and stored in the database are found useful. The same number for the wave measurements are 97%. And it shows that you can have ambitions with respect to measuring both wind and waves. We also challenged the contractor to use LiDARs with a basic outline like this. The purpose of this was twofold. First, we wanted to understand how the mean wind profile was along the tower. So we placed the LiDAR in top of the wind measurement mast, and then we're able to measure additional 200 meters up above the wind mast. And what we found is that, for instance, the mean wind is not from the same direction. It twists as you go up, and heavily influenced by the topographic feature to the southwest. And this, of course, is something that we have to take into account in detailed design. The second reason was to understand what happens along the alignment in the fjord. We measured mean value along the alignment, and here represented by the annual mean value at the 2 windmasts on each side and at the middle of the fjord. And as you can see, this is different, indicating that this is an effect that we also need to take into account. And then we also measure the coherence at the middle of the fjord. And this is exemplified with the red and green line on these graphs. And at this point, I need to say that we have in Norway a code for bridges called the N400. And these have some standard wind inputs that we can use. But it is very clear that for long-span bridges, we have to do wind measurements at the site. So the red line here is the basic numbers taken from this N400, and the green is what we measured in the middle of the fjord. So for the long wind coherence, we find quite good agreement. For the transverse coherence, there is a difference, thus indicating that if we use the standard values directly, there is an inherent uncertainty could be an inherent uncertainty in our calculations. Try just to summarize the main findings of this campaign. You have the mean wind roses, the wind roses from each of the measurement towers, and it indicates that the most frequent wind direction is from south. Actually, the highest winds is coming from the Atlantic Ocean, which is almost the opposite direction. And you can see that the terrain shapes the direction of the wind, as expected. For waves, similarly for waves, you can see that the waves changes direction due to the alignment of the fjord. The design 100-year design wave, significant wave height at the entrance is around 5 meters, but further into the fjord, it's around 3 meters. We also have a reference buoy a few kilometers further out towards the Atlantic Ocean, and this has a 100-year return period wave of 10 meters, and they go all the way out to the meteorological station in the Atlantic Ocean. They found a 100-year return period for more than 20 meters. And this also shows that it is important to measure your data at the site that you're going to build the bridge. Now, we need to, of course, take all this data and form some usable loads that we can use. So we call this environmental states. And then we look at the long-term distribution of the wind and the wave and the swell. And to reduce the number of combinations, we block the waves into units, but at the same time preserving the marginal probability. And then we merge into environmental states, and we typically have between 100 and 500 environmental states, depending on the complexity of the result of our measurements. We're now ready to start to design of the structure. And as I told you, there is a differential force on top of the tower. And of course, we want a small floater. It attracts little load, and we can have a nice, elegant diamond tower. But to compensate or handle the unbalanced load in the top of the tower, we might need to do structural changes to the tower. And to some extent, this can lead us to need to have a different floater than we expected. And of course, this will attract more load, and you get more differential force, and you have a difficult design situation. And you have to manage hydrodynamic loads, you have to manage the analysis, you have to try to find a nice architectural feature. And the next figure shows us some of the options that we have worked on in this process. We worked on the tower, we worked on different ship impact barriers, we worked on the alignment, and for these the TLP structures, we have previously seen or introduced a top cable, which is a complicated element to actually build. So in this project, we worked a lot to try to see if we can manage to remove the top cable. And we think we have found that, so the current proposal does not contain this top cable. Now, at the end, we ended up with something that we were quite happy with. And this will emerge in a few seconds. Yeah, here you have it. We take then an update and a finite element method model, and include wind, wave, and current. And when we do a design of this, we also have then hydrodynamic properties, hydrodynamic mass, and hydrodynamic damping, which modified our frequency and waves. But let's first look at some results from this analysis. The first is the tethers, the steel tubes that go down into the sea. Here's the horizontal axis period, and typically you will find wind sea forces around a period of 5 seconds. And in this case, we don't have much from wind sea for this component, and you find wind at the higher periods. What we see here is results between 10 and 20 seconds, which is consistent with swell period. And when we study it further, we see that it is surge pitch moment that initiates these dynamic forces, and it is from movement of the superstructure. But this, the dominating force will vary throughout the structure. For the tethers, this is a surge pitch. For other parts, it could be other sources. Here, we show the strong axis moment along the whole bridge alignment. And you may notice that the ultimate limit state forces stemming from wind and traffic and self-weight is about the same level as ship impact. And this is what we see in most of these projects, that these forces are around the same level. Introducing the load factors, then ULS is the driving force for our design. Up until now, I've not talked much about how we include hydrodynamic mass and hydrodynamic damping. I'm going to show another example, and here's the floating 5-kilometer long floating bridge. It has a cable-stayed bridge at one end to support a navigational channel. It has done the same extensive measurements, and the surrounding terrain is a little bit less complex, and is also a little bit more sheltered from the Atlantic Ocean. Here we see the wind rose measured at the site. And looking at this and the curved shape of the bridge, it's obvious that we need to take into account skew wind effect in our design. Now, this has been handled in detail by others, and I will not cover it anymore here, but I can confirm that we have included these effects according to their method in our design. Now, if you have this bridge and you apply wind to it, you'll start to move through the water. Then you will get added mass and hydrodynamic damping. This needs to be taken into account into our analysis model, as the added mass modified the frequency and the mode shapes, and the damping cuts out the peak of our response. Similarly, if the current or wind pushes the girder through the air, you will get some additional damping from the aerodynamic damping. Typically, the structural damping we use in this, for this structure is 0.5% of critical. But when we have decided updated our frequency with respect to the additional mass, we can go in and calculate the contribution to damping on the different modes. But first, you will see that different modes, they have driven by different loads. The blue color here indicate horizontal movement, the red is rotational, and the green one is vertical. So the slowest modes, they are mainly driven by wind, while the highest modes are mainly driven by waves. And then you have also some modes in the swell region between 10 and 20 seconds. Now, moving over to the damping, I here show the damping and the source of damping from the first modes. You see at the bottom, the structural damping. It is very small. You see that for the really low modes, you have a contribution from aerodynamic damping and viscous damping, which is around the pontoons. For the higher modes, it is purely hydrodynamic that covers the damping. And then you see that we have a valley of low damping around the swell waves, showing the importance of both understanding what the damping for the different frequency and also taking into account these swell waves. So it could be that this will inflate the swell waves, the response due to the swell waves, compared to the other modes. Now, we have an understanding of the structure, but what I did here is a very extensive amount of measurements. We got a huge amount of data. And for wind design, we are used to getting deterministic numbers and use that in design. But here we got distributions. So this figure shows the distribution. And I marked in the blue lines is our go-to values from the N400. And you see sometimes it's quite good, but other times it's far off. And we can look a little bit more into detail here. This is a typical wind spectrum. And the probabilistic distribution of the length scale, well, we got values all over the place, from 50 meter to 700 meter. Or same with the spectral parameters. And we were a bit startled. How should we handle this? We can show the effect of this. For instance, when you increase these values, you shift the spectrum to other frequencies. And that with a wrong choice of parameters, might emphasize modes that will not really be there during the operation of the bridge. So, thinking about it and maturing, we think it's a good way of doing it. Giving the designer the distributions and ask him to pick the right values that fits the actual structure that it's going to be used on. Now, we have... Oh, sorry. So, just to recap, this is the values that we expected, deterministic values, and this is what we got. It is formulated as P10, P50, and P90 values, and given as distribution. And in addition, for reference, I've added a span for the damping, and also the air density, calculated based on temperature at the site. So, we had different strategies how we should implement it. Of course, we could just pick the worst of all. And we could put mean or average or some other representative value, or we can try to include all the different combinations in our time domain analysis. The two first is very quick, but we will not know the uncertainty that we introduce into our solution. The last is really analysis intensive. Now, we're doing this analysis, we need to do 10 realization, typically do 10 realization of each analysis to remove the seed dependency. Having 500 environmental states and a million combination of a possible combination of these parameters will make it very time consuming to include directly in design. So instead we have discovered in earlier phases that we can use ordinary buffeting analysis and get an overview of the wind response, provided that we include hydrodynamic mass, the effect it has on frequency, and hydrodynamic damping. In addition, we assume that we could use a narrowband approximation, and I will show you a comparison of that later today. And we then formulated the buffeting approach so that we can use these probabilistic parameters as direct input. And we did a simulation of all of these parameters, tens and thousands of combinations, and the system do this in milliseconds. So it's very fast to get an overview of how these parameters affect the design. So this is what we got. The horizontal axis shows the result normalized with this N400 go-to value. For the top lines is for the individual component, and for the bottom line is a combination of all of the probability parameters. And for instance, the figure shows, if you go to the damping on the top, the red point shows the PET value, and the green shows the P90 value, and the arrow shows what happens in the response when you go from the P10 to the P90. So you can see here the response is decreased with the damping, which is expected. And this is the structural damping. Going to the bottom, we see that making a naive choice of these parameters could really eat out of the safety factors that we started out, without us even knowing. So we scrutinized this further, and we found out if we use the P90 value of the turbulence intensity and the P50 value of the rest, we got good results for this particular structure. So this shows the results along the whole alignment for the strong axis moment. It compares the different things I've talked about, and the green line is based on the frequency domain analysis of our system with the selected design values, while the red shows results from the time domain analysis, where we take into account full broadband response and also all the damping and non-linearities. So it's a quite good fit, and it's good enough for the purpose of selecting design parameters. So, what's next? I mean, what we looked up on is only an increment compared to what we have worked on before. And I think the answer is machine learning, artificial intelligence. This is advanced other parts of our society a lot, and we actually use it every day. You have Face ID, you have Google searches, and for instance, for medical image and medical biopsies, you now use this to identify cancer, a task that was highly specialized and done by experts before, and these systems does this better than experts. So I think this is a huge potential for the wind engineering. But what we talked about here is of typical machine learning type. You have a set of data and you have a set of results, and you try to find a fit between that using this machine learning algorithm. And the beauty of this is that if there is a connection between the data and results, it will find the connection. And it will also filter out the data you put that is non-important. You don't have to worry so much what you put in. It will find a fit. The downside is that you need a lot of data, you need a lot of testing, and you don't know how the system performs when you go out of the boundary of this. So, and for a scientist or engineer, this is not satisfactory to not know the why. And here is a way to do that, and that is to include the physics through physics-informed neural networks. What you do actually is you include the physics that you think runs your problem into these machine learning algorithms. And you find the factors, and you weigh in your physics, and you weigh in with the other factors. The benefit of this is that you need less data when you try to fit the model. And it converges faster. And it's also good that you actually have the physics in there, and you can also actually model non-linearities with respect to your physics model through this machine learning. So I think that this could be used within our field, for instance, in predicting weather or environmental states in short and long term. I think it could be useful, or I've seen it used to model flow around airfoils And it's easy to think that you can move this into modeling cross-sectional shape and optimize like flutter properties and vortex shedding properties. And I also think that it could be used to transfer synthetic wind time series to low or no structures. Now, to conclude, we have seen that we have moved our bridges, or can move our bridges from land out to the sea, and when we put our bridges into the water, we need to have extensive measurements. And I showed you that we can use probabilistic approach to extract the important values from these measurements. And I think that physics-informed machine learning have attractive properties for wind engineering. So, thank you.
Thank you very much.